Welcome back. So now we are into the final chapter of our pipeline study. From last lecture, we actually started working on pipelining hazards, the problems that we face by in implementation of the pipelining. Some of those problems, some of those hazards can be resolved by simply implementing a small forwarding type mechanism, so that it actually start working properly. Some will not work. We'll actually see how the other hazards they actually affect, how they affect the pipelining process. So what we'll learn today continued from previous, because it's actually part 2 of that pipeline hazards. We'll continue studying more hazards. One of those is actually load hazard. That is basically the data hazard, just like what we studied in the last lecture, but this time it will be load. The main source instruction is actually load one. So what happens when the load instruction, when the next instruction or the when the next instruction depend on the load instruction? So this will also lead to a hazard, but that hazard will not be able to be resolved by a simple forwarding. So this will be a problem. Similarly, we have got branch hazard. Branch hazard are actually due to the branch target, which cannot be determined before the third clock cycle, and the branch condition that also cannot be determined before the third clock cycle. So in normal process, by the third clock cycle, two more normal sequential instructions are already fetched and started execution, so which should not be there in the pipeline. So for those type of cases, so those two next instructions are used to, they have to be flushed from the pipeline to make it work properly. So the roadmap so far, the complete roadmap is basically, we are now into the final phase of this course where we studied the pipelining hazards. So this will be, so today's main topic is actually stalls and flushes. So what is stall and what is flush? We actually stop the pipeline in case of a specific hazard which cannot be resolved by forwarding. We actually have to delay, we have to insert a full clock cycle delay, so that the data is where the data is required, it actually gets ready by that time. So the stalling is basically inserting a delay or bubble in the pipeline. Similarly, flushes, in the case of branch instruction, when you have two instructions which should not be there before the branch target and decision is actually compiled in the third stage. So those two instructions, they are in the pipeline, but they should not be there, because the next instruction should have been the branch target address where it should have been fetched. So those two instructions, they have to be flushed from the pipeline, so that the normal operation, there is no change in the data. So that flushing, how we do it, how we do those flushing, that we'll study it in today's lecture. So last lecture we discussed on data hazards, simple hazards we studied, where simple forwarding actually resolve those data. The pipeline continues running at full speed without any delay, because the forwarding was fine for simple type of data hazards. But if we have got some specific hazards, like if the next instruction depends on the result of a load instruction, the forwarding will not work. So what we'll do is uh, we'll actually do something special to make sure that it stays at proper speed, but we'll have to insert some delays or stall to make it work properly. Similarly, branches affect the instruction fetch for the next clock cycle. If we have got a branch condition which is true or branch target address, so we have to flush those next instruction. So in both of these cases, we may need to slow down or stall the pipeline in order to make it work properly. So let's just do a slight review of the data headers. These are the three instructions. The result of the first instruction where the dot register number 2 is being written. The next instruction uses that register number 2 as a source. The third instruction also uses that register number 2 as a source. So what happens, we know that the fifth clock cycle is where the register number 2 is actually written in the first first instruction, but in the second instruction, in this third clock cycle, this register number 2 is needed. In this third instruction, this fourth clock cycle is where this instruction is this register is needed. So what we do is we just do the forwarding to make it work properly, and it will do without any inserting any extra clock cycle delay. But this is actually quite simple. We do the forwarding and it works properly. But what if we have got a load instruction instead of sub instruction? The first instruction, if we replace the first instruction with the load instruction, now what happens? Now the first thing is simple. We know that the register number 2 will be written in the fifth clock cycle. That is true, but will the forwarding work here? It will not. Why? Because the register number 2 that has to be written in the register, it cannot get ready, it cannot get computed before this fourth clock cycle or the memory stage. So only the memory stage computes this register number 2 value after reading the data from the memory. So we cannot forward this data which is actually set at the end of fourth clock cycle to the start of fourth clock cycle where it is needed in the next instruction. So this is something that we have to put one clock cycle. We have to move this into this next clock cycle to make it work properly. And how we do it? We have to insert a bubble, or we have to stall the the pipeline for one clock cycle. We have to make sure that it does nothing. The whole pipeline stops for one clock cycle so that it waits for the data to be ready before it's used here. So one thing you should have noticed that we are still using the forwarding. Forwarding is also used in, if we don't use forward, then what happens? If we don't use forward, we get the data straight from the fifth clock cycle. So it means we will have to make sure we have to stall for 2 clock cycles. So we'll have to do 2 clock cycles delay if we are not doing the forwarding. So basically forwarding is still required if we are stalling for load instruction. If we don't do forwarding, it means we'll have to do 2 clock cycle delay. So this is how actually this works. If we delay the second instruction, it means actually all the next instruction are delayed as well. So technically every next instruction will move 1 clock cycle on the right. There will be 1 clock cycle delay for every instruction or every next instruction, because we inserted 1 delay in the first clock cycle that was first instruction that was dependent to the previous one. So it's just a simple case that we insert a bubble. So why we call it a bubble? This is a very simple terminology, and that is related to pipeline as well. So you know, a simple water hose or water pipe, if we have some air gap inside, we see there is a bubble coming out of the hose or water. That bubble is actually an indication that there's water missing. There are some water gaps there. So that is the same thing as this gap of the data inside the pipeline. So we have got 1 clock cycle where there is nothing happening, so it means it's a bubble, just like the water bubble in simple water hose. So that's why this pipeline analogy is much like your typical water pipe or any pipelining thing that you can imagine. So now we actually need to detect the stalls. How to detect the stalls? This has to be done in actually before doing it, that we do in the forwarding. The forwarding check was actually done in the at the output of EX stage. So but for hazard, for load hazard, where we have to stall, we'll make sure that it has to start as early as possible. So we can detect the load hazard between the current instruction, which is in the ID stage. So the current instruction is in ID stage. The previous instruction, which is a load instruction, that will be in the EX stage. So we know that for a typical operation, the current instruction is in ID stage, the previous instruction is in EX stage. The previous instruction is a load word instruction. So it means that the previous instruction, which is basically where we can a hazard will be, we know that where we need a stall whenever the previous instruction is a load instruction. So how to check that? We just check the previous instruction as a load instruction if the mem read signal of that instruction is 1. So mem read is 1 means it's a load instruction where the memory is being read. This is the first condition. The second condition is now the current instruction is actually dependent on the load instruction. How to check that? We see that the current instruction, that is basically IF/ID, this register RS, or this register, this current instruction RT. If the current instruction RS or RT is actually same as the previous instruction, which is load word instruction RT, which is the destination for load instruction. So this is for load instruction, the destination is RT. So it means if we've got a load instruction and the destination is the same as the current instruction RS or RT, any of the source register, it means this will be a case of a load data hazard, and we'll have to stall the complete we'll have to stall that pipeline for to make it work. So the complete test for stalling is the conjunction of the two conditions. That is basically the first thing, we check the load word, if it's a load word instruction, the previous one, and this next one is we check the both the current source and source registers. Either of the current source registers are equal, are the same as the previous instruction load word instruction destination. So this is how you actually insert. We after detecting the hazard, what we do is we just stop the execution of that instruction for one clock cycle. So what's happening here, this next clock cycle the same thing is done, or we do nothing, so that the data is basically moved to the next clock cycle for that. Similarly, the next instruction is also moved to the next one. How it is done? We don't these are actually quite simple tasks that actually implement the stall. First task is we just don't update the PC. So the current PC value, ideally every instruction, every clock cycle, the PC is updated by the PC plus 4. What we do in this case, what we'll do in this case, we just don't do the PC plus 4, so that the next instruction fetch is not done. So this is one thing that is done. The second thing is basically we don't update the IF/ID register with the new instruction. So IF/ID register is also not written. So these two things, if we do these two things correctly, it means that the instruction is held and a stall is implemented. So just by doing these two things, the next instruction, the instruction will actually implement a stall. So the missing ALU, data memory and register write, what happens to the next phase? What happens to the ALU, the third stage, the data memory stage, and the register write for an instruction which is actually stored? So usually this ALU was actually originally, this was actually in this 4th stage. This data memory was in the 5th stage, and the register write back was in the 6th stage. What are these modules doing in these stages? Obviously they have to be doing nothing, because it's actually a bubble that is moving to the next clock cycle. So ALU is doing nothing in cycle 4, data memory is doing nothing in cycle 5, and the register file is doing nothing in cycle 6. So how to do, they are doing how to make sure that they are doing nothing? We just do one simple thing. We just clear up all those control signals to 0. But what we do is, in the second stage, the ID stage, where the the hazard is detected, what we do, we actually we clear up all the control signals for the ALU, for EX stage, for the memory stage, and the for write back stage. We just set all those control signals to 0. So these are the two things which are actually done in the hazard. So first thing we just do, we just don't do the, we don't write the PC with the PC+4. We don't write the IF/ID register to make sure that there is no new instruction in the pipeline, and we hold the current instruction. We stop the execution of current instruction, because by just putting the zeros in the control signals. So when we got all the control signals to 0, it means that data will be doing, the pipeline will be doing nothing in these stages. So this is basically a simple hazard diagram. You can see there are few inputs here. The inputs are the decision making thing, ID/EX memory that checks if it's a load instruction, the previous instruction. Then we have got the previous instructions RT, the destination of previous instruction. If the previous instruction is its destination RT, if it is the same thing as the current instructions RS or RT, which is here, so it means that it's a case of hazard. So that hazard unit will detect the hazard, and what will it do? It will first generate the two write signals, write enable signals, which will be disabled whenever the hazard unit detects a hazard. It means it will stop the PC from writing, it will stop the IF/ID from writing the new instruction. So these two things will be done if there is a hazard. Then the next thing it will do is, it will actually set up all the control signals to 0 by implementing a multiplexer in between, and set all the next control signals to 0. So that means next clock cycle, the 4th clock cycle for ALU, the 5th clock cycle for memory, and 6th clock cycle for write back, all the control signals will be set to 0, and it will be doing nothing in these clock cycles. So it's actually quite simple to implement the hazard. It will just insert a full clock cycle delay. So the hazard detection unit inputs are simple. The current instructions RS and RT register numbers, the source registers for the current instruction. Similarly, ID/EX.memory, it means that the previous instruction is a load word instruction or not. And the destination register RT for the previous instruction means the load word instruction has got the destination RT that will be detected, that will be compared with the current instruction source one. So by inspecting these values, the detection unit generates 3 outputs, but 2 outputs are simply the PC write and IF/ID write, the control write control logic, because you have to stop those write operations so that the hazard works. And a multiplexer is added for to generating the control signal, to resetting the control signal to 0 for all the next EX stage, MEM stage, and write back for this operation. So this is actually how a simple stall can insert a clock cycle delay for the whole pipeline. Another way to think about these stalls is basically your processor, your computer is doing nothing. So you can say there is a special instruction called NOP, no operation instruction. That no operation is basically a special instruction that is doing nothing. So it's just holding up one clock cycle of doing nothing. So this is something that can be done in the compiler as well. So what happens, whenever you write a program and there is a dependency, what your compiler does, instead of giving the everything to your processor to do work, what it does is the compiler actually inserts an NOP operation, or an instruction which is actually a simple instruction that actually does nothing to the some it does not write anything in any register. So it means it's a no operation instruction. So it just inserts a no operation between the two dependent instructions there where your processor was going to insert a store. So this can be done by a compiler or computer based, or your programming, where it actually stops it, avoids can your computer can avoid getting the store or hazard condition, and by just having a no operation between two dependent instructions. So this can be done by your compiler as well. So similarly, you actually do something, you actually generate a code. You can use your programming techniques, you can optimize your code so that there is no dependent instruction which actually cause a stall. So just a simple example, you can see there is actually simple C code. This is A is equal to B plus E, C is equal to B plus F, and it's a simple addition stuff. But if we write the simple code by normal operation, you can see that there are two load word operations. The result of the second load word is actually used in the third instruction for add. So first there is a load word that loads B. So second thing, it is loading E. So what is happening here, B is loaded in T1, E is loaded in T2. Similarly, later on this T4, this is the next one is F, which is loaded here. So this F is loaded in this next instruction, and so on. The next instruction B plus E, that means T1 plus T2 is done in the third instruction here. But you can see that this third instruction add, where this B plus E operation is done by adding T1 plus T2, this is going to cause a stall. Why? Because the load word instruction T2 is not ready before it's used in the third instruction. Similarly, the next instruction, it's also it's basically simply storing of data at register A. So it's just simply storing the data. That is nothing to do. There is no stall here. There is no dependency here. But the next instruction, there is this T4, and the right next instruction, there is an add instruction which actually use this T4, that is B plus F. So F is read in the instruction here in T4. This T4 is now F, and the right next instruction, this F is used, the T4 is used in the add operation to get the B plus F. So both these add operations, they actually using some data which is not ready, so there has to be a stall there. So in order to execute those instructions, so how many clock cycles we need, we can see there is 1 2 3 4 5 6 7 7 plus 4, 11 clock cycles are normal. We need 2 stalls, so that means we need 13 clock cycles to complete this code execution. But what we do is, you are a programmer, you can actually you can see there is a this whole problem can be solved by simple one small rearrangement of the code. We just do the code scheduling. We change the code so that we just put on an independent instruction between the two dependent instructions where the stall was there. So the third instruction, the add instruction, this is dependent on the second instruction. But what we do is, we just put the next load word instruction, the next load instruction right up there in the third stage where there was going to be a stall. So what we did here, we just put the load word instruction in that clock cycle, in that slot where there was going to be a stall. So this add instruction actually now gets one clock further, so that we can simply do the forwarding, and the forwarding there will not be any stall needed in this instruction. So it means, and by moving the load word instruction back, we actually avoided the next stall as well. So the next stall is also avoided. So it means that the whole instruction will be completed without inserting any stall. So it means the whole clock cycle will be completed in 11 clock cycles, which is the default one. So this code scheduling is another method that we can actually avoid the stalling by simply changing the code. By this is actually something that is done in the software part. So now the next part, the second part, this is your about the control hazards that are done due to the branches. So what happens in the branch instruction, we all know that branch instruction jumps to a next, the program counter will be updated with a branch target address when the branch condition is actually true and the branch target is calculated in this third clock cycle. So this is the clock cycle where the branch target address is calculated and branch condition is checked. But what happened in the pipeline, this is the third clock cycle, but before this decision is made, we already have the next instruction loaded in the next clock cycle and the next instruction loaded in the next. So we already have two clock cycles, we already have two instructions in the pipeline before this decision is made. And what if the decision made is we have to jump, we have to branch to the branch target address. So it means that the next two instructions which were loaded, which were already in the pipeline, they have to be deleted from the file so that it works properly. So most of the work for a branch computation is done in the EX stage. We know that the branch target address is computed and the sources are compared and the zero flag is set to be cleared accordingly. So thus the branch decision cannot be made until the end of EX stage, and by that time there are already two instructions in the pipeline. What we do now, we have to stop those instructions or doing to make sure that the next instruction. So one thing that can be done is to just stop execution when there is a branch instruction. So the next instruction, the PC plus 4 is done after the decision is made. So we just hold up 2 clock cycles. This is one solution. We just put stall. So stalling is the one solution that we just stop the execution till the decision is made. So this is actually one of the solutions, but it's not a very effective one. Why? Because we are actually holding up 2 clock cycles for that. So we just have to wait until the clock cycle number 4 to execute the next instruction. So what's next? What should be done? What's the better solution here? So there are a few things that can be done. One of those is actually branch prediction. So another approach is to guess whether or not the branch is taken, or this way if we've got a good prediction, if our prediction is correct, then it means that the normal operation will keep going. If our prediction is wrong, then it means that we'll have to do some extra penalty that will come with it. So in terms of hardware, it's easier actually to assume that branch is not taken. So if we just set up a prediction that branch is not taken, it means that the branch condition which the decision will be made in the third clock cycle. If we predict that the branch is not taken, it means the normal case, next instruction 1 and next instruction 2 will be executed as normal, and if the prediction is correct, that it means that these two instructions are usually what should be the next instruction in line. So this will be correct. We won't have any extra delay or stall if we have got the correct prediction. But if there is if the prediction is wrong, then it means we have to remove these next two instructions from the pipe, so that the the pipeline is back to normal. So the next instruction that will be fetched, that should be the branch target address, the label that is decided in the third clock cycle. So this will be the penalty for this misprediction case. So with prediction not taken, the normal case it will execute normally. If the prediction is incorrect, then it means we'll have to insert the bubble. So this bubble we actually do something better. We actually change the reliance so a little way so that the branch the design, the structure of the branch, the data path for branch instruction is actually uh, it can be optimized by just doing few little things. So usually all the modern CPUs they use branch predictions, and this is actually quite a important thing that is used. There are different techniques of branch predictions, not the simple like not taken and taken and just the simplest one. There are a few advanced method of prediction. So overall branch prediction is totally worth it. Mispredicting a branch means that two clock cycles are wasted in normal cases, but we can actually reduce this if by just changing a little bit in the datapath that will actually study in the next slide. The pipeline structure also has big impact on the branch prediction. The more longer and bigger, deeper pipeline will be, it will be much more problematic than simpler one that we are actually studying here. So implementing branch, what we do is we actually move a bit of the units, the functional units that were used to decide the branch and calculate the branch target address. We can do both of these things in the second stage whenever there is a branch instruction. So the branch target address, we can move that to the second stage because we have already got all the things there. We also can do a simple comparison. The subtraction stuff that was done in the ALU stage, that we can do in the second stage as well. So both of these things, if we move these to the second stage, so it means that we don't need this third stage branch calculation. So all these can be done in here. So if there is a misprediction, we just need to store one instruction, or we just need to flush one instruction instead of two like before. So this is something that is actually a good optimization of the whole one. So how to implement the flush, that is important. We must flush one instruction because if we moved it earlier, if the previous instruction is branch equal and its two source registers are equal, we can flush an instruction from the IF stage by replacing it in the IF/ID pipeline register with a harmless no operation instruction. Why a no operation instruction is basically just replacing the current instruction with an instruction that is doing nothing. And what is that type of instruction that is doing nothing? It's actually a simple instruction SLL, shift left logical 0 0 and 0, both the register destination 0, which is actually not possible, but register source is 0 and we just shift it left. If we just decode it into machine code, it means all the zeros. It is just a simple replacing every 32 bit of the machine instruction. We just replace it the current instruction into a 0 instruction. So that means the current instruction will be replaced with the instruction that is doing nothing. So the next time it will be doing the instruction. Basically the PC will be updated with the branch instruction. So whatever the instruction that was in the pipe, it will be flushed out. Similarly, we can flush the other instruction which is in the ID stage. So the IF flush control signal is shown. It actually flushes the whole instruction. So the whole, you can see in the red, the branch target address calculated is moved to the second stage, and also the comparator which is done here. So the register read, this is the comparison thing. Both are the things which were previously done in the third stage, that is done here. And the flush register, we are not talking about how this one is generated. We're just seeing if there is a branch in this case and we need to flush. We just set up this whenever this is this flush bit is set, flush control signal is set, we replace the instruction with the all the zeros, so that the next instructions are doing nothing in the program, in the whole pipeline. So this is how we actually flush the pipeline, flush the instructions from the pipeline in the cases we have got a misprediction in branch. So we have studied both load headers and branch headers where the stall and flushes are implemented. So a few little things before we complete the package, we complete this whole topic. There are more realistic branch prediction rather than just the not taken branch prediction that we just studied. There are static branch prediction where we actually base it to a typical branch behavior. For example, in the loops, we know that most of the time the branch in a loop is actually already almost taken most times. Unless the last iteration of the loop where it's actually going to break. So it means most of the time the behavior of a current or certain branch instruction will be same. So the predict backward branch is taken, predict forward branch is not taken. So these things can be decided, can be actually set beforehand by just seeing how the behavior of a certain type of branch is. Similarly, we have got a dynamic branch prediction where actually hardware measures the actual branch behavior. It records recent history and changes accordingly. So the branch prediction will change from taken or not taken by just checking the last or the history of that specific branch. If the last time it is taken, it's more likely to be taken again. If it's almost every time it's changing the behavior, then the dynamic branch prediction will not work as efficiently as it should. But if it's behaving normally, so it means it's more likely to behave the same way in the next instruction. So the previous history matters. So dynamic branch prediction is when the previous history of each branch is actually taken into account by before actually predicting the behavior of that specific branch. So in deeper and superscalar pipeline, branch penalty is actually more significant and it will affect the performance of the pipeline processor. So for that, dynamic branch prediction is used. So we use the hardware actually gets specific hardware registers to actually store to store the branch prediction data in a buffer, and they are indexed, and that is actually used to do properly. So we just see how a single bit branch predictor works. A single bit means it's just taking a simple value that if in the last time if its value is if the branch is taken, it will set to either 0 or 1 for taken or not taken. If the last time it's taken, so it means it will be set to taken, and again the next time it will predict taken. If we've got a branch prediction wrong, it will change to the not taken, and next time it will predict not taken accordingly. So mispredict as taken on the last iteration of inner loop, then mispredict as not taken on the first iteration of inner loop. So in this scenario, you can see that this prediction, simple one-bit predictor, will fail the next time it changes the misprediction loop. And the 2-bit predictor, the dynamic 2-bit predictor, will actually not change the behavior of the specific branch until there are two mispredictions. If there are two successful misprediction, then it means the branch behavior is changing. If the branch prediction, the branch behavior will change from taken to not taken only if there are two not taken. If two misprediction, so we predict the predictor predicted taken, and there are two successful cases where the branch is actually not taken, so that the next time the value the predictor actually stores it as a not taken. And similarly, from the not taken, it will only move back to taken whenever there are two misprediction on this scenario. So this will not change in every misprediction case, like in a single bit predictor. So these are actually prediction is quite a big topic. We can actually study more. You can do one thing, that just read a bit about it in the book. So this is actually where we wrap up the our topic. The pipeline is going to be wrapped up. You just increase your, you can improve your actually concept by doing some exercise problems similar to what we did in the example. You can you can actually solve different exercise problems by just understanding the whole thing about pipelining. So this is a summary, the three kind of hazard that we actually studied. Structure hazard are the hazard where there is not enough hardware available, like we have got a single memory or a single ALU, so that won't work. We will need more hardware, or we'll have to change the whole pipeline process according to that specific hardware. So this is an example of structure hazard. Similarly, we have got data hazard, where the next instruction is dependent on the current instruction, or the current instruction is dependent on the previous instruction, and for that some instructions can be resolved by only doing forwarding, and some instructions we have to insert stalls to get it work properly. So then we have got control hazards, that is branch hazards, where the next instruction that is going to be fetched, that needs to be done properly. For that branch instructions, we can predict, we can do prediction, we can do different types of prediction to make it actually work better. So these are the different cases for headers. So that's actually the wrap. Now the next thing will be your exam. Before exam, I suggest you do some exercises so that you are well equipped for all the problems that are going to be you are going to face in the exam. So next time we'll discuss in a couple of sessions that are left for your discussion sessions. So we'll discuss some problem there. So please try to be there on Friday. Okay, bye.